Welcome back to another lesson. Today we finally conclude our three-part series. If you haven't seen the first two, I would recommend you go back and watch them first so you have a better perspective of the big picture. That being said, you should remember this table from the last lesson. If not, I advise you to go back and revisit that to jog your memory before we continue. To reduce some of the clutter, we can rewrite that table as a matrix, as seen here. This is a simple bookkeeping exercise in linear algebra. If you are not well versed in that topic, the details of this lesson may not make a whole lot of sense. Nevertheless, we will try to explain the main points as simply as possible, so please bear with me. In part 2 of this lesson series, we multiplied each Taylor series expansion by a coefficient. In that case, I gave you the answer and showed how it worked out to give us what we wanted. In reality, these coefficients are unknown, and we have to solve for them. They are labeled A, B, C, D, and E. To solve the coefficients for the first derivative, which is highlighted in red in the second row on the very right, we must add the terms in the second column of the matrix and equate them to 1. For every other column, we must add the terms and equate them to 0. This is represented in equation form on this screen. The second equation is highlighted in red and corresponds to the second column of the matrix in the previous screen. Feel free to pause the video for as long as you need until you see the connection. Now I can factor out the coefficients to form this matrix representation. Once again, it tidies things up and makes the bookkeeping a bit easier. That was the thorough process to get here, but to make a long story short, it turns out that the matrix we just obtained is simply the transpose of the first one we saw. In the future, using this shortcut may be an expedient option. For those who are not familiar with what a matrix transpose is, it is simply switching the rows and columns. I've used color coordination to guide your eyes. To solve the previous matrix equation, we must find the matrix inverse. I use computer software, specifically Microsoft Excel, but you are free to choose any method you prefer. The product of the inverse and the vector yields the coefficients for the first derivative, which we saw in part 2 of this lesson. They can be written out like so and rearranged into the familiar form. Refer to part 2 of this lesson if you need a reminder. You may have noticed that since we have a 1 in the second row of the vector, that is equivalent to reading off the second column of the matrix. That is an astute observation, and I commend you if you noticed that before I mentioned it. So what happens if you shift that 1 from the second to the third row? Well, you get the coefficients for the central difference approximation of the second derivative. Similarly, moving the 1 to the fourth row corresponds to the third derivative. Notice that this is now a second order approximation, unlike the previous two, which were fourth order. Lastly, moving the 1 to the fifth row of the vector corresponds to the fourth derivative. This is also second order. I have pulled this summary table from Wikipedia, which organizes the coefficients quite nicely. In red, I have highlighted what we just found. The green box represents what we found in part 1 of this lesson series. What other patterns do you observe in this table? And why do you think that might be? How about those other rows beneath the red boxes? How do you suppose we can find those coefficients? Don't hesitate to pause the video for a moment if you need some time to reflect on these questions. Well, to do that we're going to have to expand our table to include x minus 3h and x plus 3h. That can be seen here. I have highlighted in red the portion of the expanded table that doesn't change from what we used before. Taking the transpose of that matrix and then the inverse, I get the following result. I leave the details of these operations for you to explore on your own. Similar to last time, we can simply read down the columns to get our central difference coefficients. Those are highlighted in blue on this table. In order to obtain those higher order approximations, we would need to enlarge the table again. This time, it would have to include x minus 4h and x plus 4h. I do not present that in this lesson. However, you are free to pursue that on your own. So that concludes my discourse on central differences. What about forward differences? We haven't mentioned those in a while. Forward differences can be obtained by cutting this block out of our larger table. That's the shortcut method. If you're confused why it's so simple, the reason boils down to the Taylor series expansions seen on the first screen of this lesson. In this case, we would truncate each series after the second derivative. The matrix form is represented on top. On bottom is the inverse of the transpose. Reading down each column gives us the coefficients we need to compute the forward difference approximation. The second column corresponds to the first derivative. The third column corresponds to the second derivative. We can get a higher order approximation, and also a third derivative, by cutting out a larger block. The same rules apply as did the last time. This is the matrix form on top, and the inverse of the transpose on the bottom. Just like last time, except we have a 4x4 matrix instead of a 3x3. Reading down each column gives us the coefficients we wanted. All that is summarized in this table, which came from the same Wikipedia article as the central difference table. To get higher order approximations, what would we need to do? If you answered, add x plus 4h to the table and cut out a 5x5 matrix, then you are correct. I omit the details here. Regarding backward differences, the process is very similar to finding forward differences. By now I'm tired, so I won't do that either. If you would like to explain the details how to do that, feel free to utilize the comment section below. Otherwise, thank you so much for watching. I hope this 3-part lesson series added value to your understanding of finite difference methods and how we can obtain them from Taylor series expansions. If you enjoyed this lesson, I ask that you find a friend or two who would also benefit from this teaching and share the videos with them. Thanks again. I will see you next time.